in terms of dealing with real problems was the least mean square error. So instead of considering good or bad classification, please help me to answer, because I don't see the answers of the, if someone says something, I cannot see it easily. So please help me. Okay. What I was saying. The least mean square error, it's able to deal properly with overlapping, converting a problem of exact, correct, and correct into a, well, more or less differences, deltas between desired target values and what you really obtain with your functions. As there is always a difference, then you try to minimize these differences. Okay? And this allows us to smooth conveniently the problem. This has to be combined with the activation functions. We almost haven't talked about activation functions. You have some information of activation functions in the slides, but it's not the same if in your linear function you put an activation as a sigmoid, which converts the outputs to continuous values between 0 and 1 or 1, 1. This is one thing, but it's very, very different if you use an activation function as the rectified linear unit, which means 0 if the output is negative, nothing, the output is positive. Be careful, because in the implementation in scikit-learn, by default, the activation function is 1. In certain cases, doesn't matter. But depending on which are your target outputs, you have to fix the target output when you give the training set. For example, if you use an activation function that converts your output into -1, 1, but then you put your input, your training examples of classes, and you put 0 and 1 as desired values, it's not going to work. Okay?
I don't understand, because you say if it is negative, you get a 0, no?
Well,
and if it is possible, you get nothing. What do you mean it doesn't convert? So,
well, that's the thing, or converts to a result that is arbitrarily bad. Let me put an example. An easy one. We are still talking about the previous model, but I mean, I think it's important. You remember that we can have, for example, in one dimension, imagine a problem with two Gaussians, class 1, class 2. And we use a simple neuron with an activation function which is like this, rectified linear unit, which is the identity for positive outputs and 0 for negative outputs. If our problem is like this, we can start with an arbitrary weight vector. We let the algorithm iterate, and then there will be a minimum for which the square error will be minimum. First of all, do you agree that if the activation function is nothing, which means the identity. Let's assume first the identity, so no activation function. Let's assume that we label our classes are +1, -1. +1 is +1, +2 is -1. Okay? Then, because these are Gaussians, most of the inputs are accumulated into the means of the two classes. It means that the linear function that will be obtained, the one that minimizes the square error, would be a linear function that is something like this. In such a way that for the value of the mean of class, let's say 1, this value would be +1, and for the mean for this class, this value will be -1. This is the linear function that minimizes the mean square error for this problem. But if I label my training data as 0, 1, instead of this linear function, okay, instead of this linear function, I will obtain this linear function. Because for inputs close to this mean, the value will be 0, and the other will be 1. Depending on the activation function, I will obtain different solutions. Okay? In the same way, if instead of this linear function, this activation function, sorry, I will have, for example, a function like this with -1 here, +1 here. This would be, for example, the hyperbolic tangent function. In this case, depending on the particular shape of this function, then I will obtain a function like this, or like this, or like this, depending on this. Sorry, depending on the particular shape of this function around 0. Okay. But if I have an activation function which is 0, 0 for negative outputs, inputs, and then the identity, this is the ReLU function, then it's impossible that I have -1 as desired output, because the minimum possible output is 0. Okay? So by changing the shape of the activation function, you can have different values. Okay? Well, apart from that, you dig a little bit on the implementation, you will find out that the least mean square criterion is only used for regression, not for classification. That's because for classification, instead of the mean square error, it's better to use the so-called cross entropy. But I mean, this is a detail. You can dig a little bit on that. The criterion we have studied for classification is the one which is implemented for regression. Can be also used for classification, but usually it's better. That's why it's used by default. So we have different changes with regard to what we have studied. But more or less, the main things remain. At the end, we look for a minimum of a criterion function, which is smooth and that is sort of controlled also by the last activation. Observe that activations between layers are in principle more irrelevant for that, because in the internal layers, the activations, the weights of the forthcoming layers will adapt to the outputs of the activation. But the last activation have to be compared to the target values we fix. So you have to know which one is your last activation, then you have to fix conveniently your target values. Usually, in implementation, this is done automatically. So usually, you don't have to care about that, but you have to know. Okay? Any questions about formulation? Remember that at the end, we are learning the weights of a combination of linear functions. The problem is a simple optimization problem in which we compute a gradient and make corrections. Okay? Also, remember that in our problem, we have we have more degrees of freedom because any weight vector can be multiplied by any constant. So that depends also on the activation function. But usually we can multiply the weight by a constant and the function changed, but the classifier is the same. Okay, now we could go a little bit ahead on the new formulation. Do you remember the concept of margin we introduced when talking about linear separable problems? Margin is the distance, or anything related to this distance, the distance between the minimum distance between an example, a given class, and the decision boundary. For example, if we have a linear separable problem as the one we have in the slide, you can see there 3 different classifications. There are 2 of them that whose margin corresponds to the radius of these little circles you see drawn there. We could even have a classifier even with a smaller margin. For example, this one. This new classifier, if I plot it correctly, is a classifier that in fact separates the data with margin 0. On the other hand, let me delete this. On the other hand, we have this other classifier, as you can see, whose margin is larger. You see? Now, let me pose the following question. Which of these three, imagine this margin B is even smaller. Imagine that is even smaller. Given these three classifiers, which one do you think that would be best? Best in terms of that would be able to generalize better. Which one do you think is best? We can even exaggerate this. We can have one class here, another class here, class 1, class 2, and then we can think of this classifier with little margin, or this classifier with much larger margin. Which one is best? Vertical one. Do you all agree? Why? This is impossible to answer without more information. Because, I mean, looking only at this data, if nothing else is said, there is no objective answer to this question. But usually, if our training data is whatever we have, usually the test data, the general data, the true division of the classes would be something similar. It can be proved, we are not going to do that, but it can be proved that the larger the margin, the better the generalization ability of the classifier. This is like a general principle, not only for this kind of functions, but for more general classes of functions. In other words, if I'm able to separate data with a much clearer separation between the two classes, the clearer this separation, the higher the probability that when seeing new data, the classifier continues to classify the thing good again. Okay, so again, this maximizing in some way the margin obtained when separating the data, it's a good thing to have classifiers that will behave better on test data. Can you understand that? I mean, we are just announcing this and trying to look intuitively that this is a good thing, nothing else. Huh? Well, if we more or less understand that, then instead of using the margin as a fixed parameter, as in the previous approach, because in the previous approach we can use margins, but as fixed things. What if we add the margin as another parameter that we can try to optimize. Why don't we maximize the margin? Why don't we formulate the problem? Let's find for the linear function that separates the data with maximal margin. If we were able to formulate this, then we will have another optimization problem. Okay? Let's see how can we do that. Okay? What would be the advantage? The advantage is that the linear function, the linear classifier we will obtain, it will be a linear classifier, but we will have a guarantee that this function would be a better generalizer. In order to do that, we need to go back to the formulation of our linear functions. I assume all of you remember and everything. I mean, the weight, the linear weights, the bias term, the z's is the functions because we fixed that we have only two classes. One class is +1, the other class is -1. This way, the formulation of the problem becomes this. G is the name of the linear function, and B is the margin, or the parameter of the margin. If we write this condition there, then it means that all the points will be well separated and at a distance from the boundary greater or equal than B over the norm of W. Okay? But as we recalled, any weight vector can be multiplied by any constant, and the boundary is the same. Okay? This was a degree of freedom that was left there in the other formulation. But it wasn't a problem because at the end, we use an activation function and we minimize the error, and that's all. Then the model converges. But now we are going to do things in a different way. So in order to formulate what we are going to formulate, we could, for example, maximize B over the norm of W, which is the distance from the boundary for all points, which means the minimum of that. But instead of that, let's assume that we fix the value of B equal to 1 and then we can write the above condition in this way. I don't know if this is clear. Imagine a positive point, a negative point, all of them in one dimension. Okay? Assume a linear function that separates these 2 points. For example, I don't know, this or this or this. All of them separate the points. But what's the important thing? The important thing is the boundary. So instead of linear functions, let's consider boundaries, either this boundary or this boundary or this boundary. And for any boundary, uh, for any boundary, adjust. For example, for 2 points, the best boundary would be the middle point. Okay, let's fix the middle point. Oops. Let's fix the middle point. This is the middle point. Any function, linear function, that goes through the middle point is the same boundary. But from all these family of functions, I can take the one that gives +1 for this and -1 for this. And I can always do the same thing. Imagine any number of negative points. Imagine any number of positive points. Suppose that the problem is linearly separable. Then take the 2 points that are the closest, in this case these two, go to the middle point, and then adjust a linear function that gives +1 for the closest positive and -1 for the closest negative. And that's what we are saying in this equation. Imagine that you have 2 dimensions instead of 1. You can do the same thing. You can take the linear function that leaves this point will be the closest from this side, and this, which will be the closest for the other class, and then adjust this linear plane, because now it will be a plane, adjust this linear plane in such a way that you've got +1 for these points and -1 for these points. You see? We can always, let me draw it again. We can always draw or consider that our linear boundary is, imagine you've got a wide imagine that our goal is to put between the two classes a wall as wide as possible. This problem, the widest wall would be the one I have plotted, for example. Then this wall will correspond to a linear function that on one side of the wall the value is -1, in the middle of the wall the output is 0, and on the other side of the wall the output is +1. You can always do that if the problem is linearly separable. What would be then the distance if you adjust the function like this? What would be the margin in this case? Because you have adjusted the value of b to be 1 +1 -1, then in this particular case, the distance, the margin, in fact, would be 1 over the norm of W. Okay? Well, you can think of this as if it was a trick. Doesn't matter. We are not going to dig into the formulation, but you have to understand the concept of the margin. And more importantly, the kind of optimization problem we are going to obtain. It's more or less clear. We can formulate the same problem in a different way, but now the goal is to put into the classes, between the classes, a wall as wide as possible. And the width of this wall is what we want to maximize. Okay? If the problem is not linearly separable, the problem has no solution. Then we will see what we will do. Okay? Here you have another problem, another visualization of a problem of two classes. Red points are class 1, blue points are class 2. I'm afraid that I'm using class 1 for class 2 and -1 for class 1. Doesn't matter. As we can see, in this case, we have a linear function that leaves 2 points of one side and other 2 points on the other side equally far away from the middle point. For this problem, we can adjust the linear function. Think of the linear function, in this case, as a plane that cuts the figure in the black line. But the slope can be different. So we adjust the slope in order to have the value of +1 along this line and -1 on the other line. Obviously, because this is a linear function, we have 0 in the middle, the boundary, in fact. So this is the boundary, and sometimes we call all this region, formally, we call this the margin. The margin, in fact, is the distance. Okay?
So we have to think it as a plane, and for example, I mean, you have that line that is a discriminant function.
The black line that was here.
And here, -1, when it's the red class, so you will have this shape in the plane.
No, it's a plane. I mean, the plane will be like this, negative. So it's
and you
positive
say,
and negative.
I give this -1 and I give this +1.
Yes, because this plane, I can multiply this plane by the constant I want. So I adjust this plane in order to have +1 here, -1 over there. And because this is a linear function, if I have 0 here, I have 1 here. If I move the same distance inside on this line, the output will be +2. And at the same distance, the output will be +3 because it's a linear function. Okay? And the same on the other side. Here I have -2, -3, and this will be the contour line of the function. The contour line in this case are lines because it's a linear function. Okay? Once we understand that we can do that with the linear functions, and knowing that we want to optimize the margin, the widest wall we can put between 2 groups of points, then we can formulate the problem this way. because we want to maximize the margin, and the margin is 1 over the norm of W, is the same that minimizing the norm of the weight vector. Observe that for the multilayer perceptron, for the other formulation, we used the whole weight vector, including the bias. We don't have the bias here. The bias plays another role here. This weight vector is the weight vector without the bias. That's important. But you see that this norm of W, minimizing this corresponds to maximizing the margin. That's the thing we want to maximize. Minimize in this case. It's okay? But also, we have to be sure that all the points are on the correct side, which means that this equation that we had using b equal to 1, because I fix that I want only functions that give the minimum positive output is +1 and the maximum negative output is -1. This is a requirement I put the problem. So I'm requiring that for all input points, the output of the function is this WTX plus the bias multiplied by the corresponding label, +1 -1. This has to be greater or equal than 1, which means greater than 1 for the positives, smaller than -1 for the negatives. What's that? This is an constraint optimization problem. It's a problem with restrictions. As an optimization problem, this problem is very different from the previous one. The problem we had before, it was an unconstrained optimization problem. We only had a criterion, and that's all. We compute the gradient and we adjust. No restrictions. Now we have a criterion, is this norm, square norm, but subject to have restrictions. And these restrictions, this is a linear function. So these are linear restrictions. Okay? And this norm is nothing but a quadratic function. You can write this norm also like this. Well, sorry. Yes, because it's squared. It's okay? So we have, for a linear classifier, we have formulated a quadratic optimization problem with linear restrictions. As many restrictions as points in the training set. Is this problem easy, complex? Well, something in between. These kind of problems are called, quadratic problems with linear constraints. The standard way of solving these optimization problems with the method known as the Lagrange multipliers. We are not going into details, but we need at least to have a look at some steps. I insist. We don't need to go to understand all the mathematics. You can You are welcome to do that. But it's not the goal of our course. The goal is to understand the model, but to understand the model, we need at least to point out some of the particularities. The first one is that it is a constraint optimization problem. The second one is that we have standard solvers implemented in many systems. We can use standard solvers, but instead of that, specific solvers have been developed. In particular, the standard way to treat these problems is to go through, well, basically the idea. The idea of the Lagrange multipliers is that we can convert each of the constraints into an additional term in the criterion we want to optimize. Which means we can take this restriction, convert this restriction into a subtraction between, we have zgx greater or equal than 1. We can put this minus 1 greater or equal than 0, and then we could minimize the difference between g of x and 1. That's exactly what is done. And then we have something like this. This is called the Lagrangian of the problem. And now, of course, each restriction, which is added to the criterion, will carry out a constant or a multiplier, which is this alpha. You see, I'm talking about this because this turns out to be important in the interpretation of the model. This alpha is a multiplier that weights the importance of each restriction. All the restrictions have to be fulfilled. But at the end, we modify our problem and construct another problem using this Lagrangian. By the way, I have introduced an 1/2. It wasn't there, but anyway, it's just a constant. And an important restriction is that these multipliers have to be positive. Otherwise, we are not minimizing what we want. Anyway, following the standard thing, we will arrive well, as we want to minimize this, the following steps will be to obtain the derivative, the gradient of this, and then write the equation, the gradient of this equals 0, because for the minimum of this problem, the gradient needs to be 0. In very easy problems, you just write this, compute the derivatives, equate to 0, and then you obtain a set of equations, and the solution of these equations is the solution of your problem. But in this case, it's difficult, and what we can do is we are going to see the result. But at this point, we are going to introduce a very important definition. Remember that z is +1 or -1. Given a weight vector and a bias term, once this is fixed, we define a support vector as any point x such that the output of the linear function is either +1, -1. In other words, if we have a linear function, if we have a wall between our two classes, the points that touch the wall are called support vectors. Okay? For example, if you have this set of points of two classes, and you have this linear function, the one that corresponds to the black line and the one that gives output +1 for these points and -1 to these points, the points that are circled are the points whose output is +1, +1, -1, -1. These are the 4 support vectors corresponding to this problem and this function. Observe also that given a set of points, the function that maximizes the margin is a unique function. There is only one linear function that maximizes the margin. So once you have a set of points, linear separable ones, it exists a unique linear function that maximizes the margin, and it exists a unique set of support vectors. In this case, these two. Okay? If you have a set with only one positive point and only one negative point, which are the support vectors? Only 2 points, one positive, one negative. Which are the support vectors for the optimum linear function? Two points are always linear separable. Which of these 2 points are support vectors? Put a wall between 2 points. The widest possible wall between 2 points. Which points touch the wall? The 2 of them. If you only have 2 points, one positive, one negative, the 2 of them have to be support vectors. Let's imagine 2 positives, 1 negative. Which ones are support vectors? Are you sure? Someone has said something? The positive, the negative, and the positive. Only the closest to the negative would be a support vector. So you think that this is... It depends. Given a set of points, the optimum linear function, in our sense, is unique. So it doesn't depend on the function. It has to depend on the points. But in fact, it depends on the point. If this point is, for example, around here, not here, then the margin but if this point, instead of being there, is here, in this case, you only have two supervectors. So if you have 3 points, it can happen that the 3 of them are supervector, or perhaps only 2. The same with 4. With 4 points, you can have the 4 points in a line, and then only 2 of them are supervectors. But if they are, I don't know, depending how they are, you can have the 4 of them supervectors, or perhaps only 3, perhaps only 2. Okay? But important, once you have the set of points, you have a unique solution with maximum margin. And this unique solution corresponds to a fixed number of supervectors. Okay? And now, a very important fact that comes from the theoretical solution and formulation. We are not going to go into details, but I'll try to explain intuitively. Observe this problem here. 1, 2, 3, 4, 5, 4 and 5 points, 9 in total. Okay? For this set of 9 points, the optimal solution is the one that you have plotted here. Okay? The supervectors for this case are the 4 you have circled. Okay? Now imagine that instead of the 9 points, you start only the supervectors. What will be the solution? Exactly the same. Now imagine thousands of points. You have thousands of points in each class, linearly separable. For these thousands of points, you have a unique optimal solution. Imagine that you have this solution plot here. Imagine that this solution has hundreds of supervectors. Imagine hundreds of supervectors. Now take out all the points that are not supervectors. And you have exactly the same solution. What this means? What this means is that the optimal solution only can depend on supervectors. You don't know initially who are them, but the solution has to depend only on supervectors. Now, perhaps it can be easy to understand that once you go on, you manipulate the solution. I'm not going into details. You, at the end, convert. Look, this is the problem using the Lagrangian. These are the multipliers. Remember that you have a 1 multiplier for each restriction, which means 1 multiplier for each point. This problem can be changed into the so-called dual problem of details, which is a problem that is formulated in this case. You are looking for a weight we are looking for a weight vector. And in the dual problem, you are looking for an alpha vector, which means a set of alphas. These alphas are the other alphas. With restrictions. So at the end, you are changing one quadratic problem by another quadratic problem. A problem on weights into a problem on alphas. What's the point? Well, the thing is that this problem on alphas, we only have a very easy restriction, which is this alpha positive, and a unique restriction, which is this sum there. In this case, the problem is can be solved more efficiently, but we don't have to understand that. What we have to understand is that the solution of our problem corresponds to obtaining these alphas, which mathematically, but also intuitively, have to correspond to check, obtain, which are the support vectors. In other words, on all this formulation, the important one that you have to remember, well, not remember in the sense that you have to know this equation, I mean, that you have to observe is this one. This expression here relates the weight of the primal problem, the vector of weights, and the relation to the alphas, the multipliers. The optimal solution will correspond to a weight, but this weight can be obtained from the alphas. But in this expression, as the solution has to depend only on supervectors, this means that the alphas associated to non-supervector points have to be 0. In other words, for this problem, which has only 4 supervectors, the weight of this optimal solution has to be a sum of only 4 terms. 1 term for each support vector. So at the end, solving the problem consists of obtaining alphas corresponding to support vectors. Okay? We don't have to learn now how the problem is solved. There are algorithms for that. But these algorithms, what this algorithm gives us, this is implemented in scikit-learn, is the alphas. So we need to interpret what the algorithms give us. The algorithms give us the alphas. So if we have 9 points, we give these 9 points to the algorithm. The algorithm gives us 9 values of alphas. 4 of these values are non-zero, the other ones are 0. We only have to care about the ones who are not 0, the supervectors. With these 4 alpha values, we can compute the weight vector and the bias. Okay? And this is the standard formulation of the so-called supervector machine. And the name supervector is because at the end, the solution depends only on a few input vectors. Okay? Questions? In the next class, we will go through the implementation of scikit-learn. The implementation of scikit-learn is very well documented. You can go through the documentation if you want. You can try. There are examples. We will have a look at some examples. But the most important thing would be to explore what the outputs that the algorithm gives us, how can we interpret these outputs? Because we can just take the object and then we can use the object for classifying and then obtain results, and that's all. But we would like to interpret what's happening. On the other hand, this model, what we have seen so far, is not useful in practice. Why? Because this only works for linear separable problems. Okay? So the first condition is that let's have a linear separable problems, which is something ideal. Is more or less clear intuitively? Okay, if this is clear, now what can we do if our problem is not linearly separable? For example, two Gaussians. We have two Gaussians overlapping. We know which is the best solution. It has to be to leave most of the points of the Gaussian on one side and most of the points on the other side, but certainly there will be some overlap. So how can we manage now our margin concept in this case? Well, if you find what we have up to now strange, the following step is far more strange. The next step is what is called the soft margin formulation. Which consists of the following. What you have now in the slide, it's two sets of points, red ones and blue ones. As you can see, this problem is not linearly separable. There is no linear function that can be put between the two classes. That's impossible. Well, but we can plot any linear function, adjust this, the same linear function can be adjusted to have, for example, the value +1 and -1 far away or not. For example, in this case, we have a linear function which gives you output 0 here, +1 here, -1 here. We could have plotted differently just by multiplying the weight vector. Okay. For this situation, here we have points that are well classified before. We still have, in this case, points that touch the wall, and then we have some points that go inside the wall. The strategy we are going to use is to allow some points to get into the wall. That's why this is called soft margin. But the more points go into the wall, the worse is the solution. How can we measure this worst solution? Well, because we are going to change the criteria. Instead of minimizing the norm of the vector only, we will be also minimizing the number and strength in which points enter into the wall. Okay? This is done to be able to do this in a convenient way. What we use is something which is in fact standard in optimization. What we are going to use is what is called slack variables. We are going to introduce a slack variable for each point. This slack variable is a value which is positive, and remember that the previous constraint, the constraints we are considering are the ones we have here for t equal to 0. When t equals 0, we have what we had before, t equals 0. But now we introduce a positive t there. So 0, t equals 0 means this point is touching. Well, in case of equality, t equals 0 means touching the wall. T equal 0 okay, and then when we move into the wrong side, we allow the point to get into the wall, and there is no limit. I mean, you can take a point and go on the wrong side as far as you like. You see? But then the higher the value of this chi would be variables that are going to be optimized as well. And at the end, we are going to formulate the problem as follows. Instead of minimizing only the norm, we are going to minimize the norm and the sum of the values of all chi. Remember that chi are positive. Multiplied by a constant c. That's a constant, pre-specified constant, because we are comparing different things. The values of these penalties, which depend on many kind of things, and the norm of the vector, which is a different thing. So this c, it's a constant. And the restrictions are the same, but with this chi value. Okay? If a problem is linearly separable, then you don't need any chi. All chi's would be probably zeros. Okay? But this will also depend on the value of c. Because now the problem is more general. You have more variables to optimize. But at the end, for example, once you fix C, then you will have a solution with more going into the wall or with less points entering into the wall. Okay? Imagine that you don't have these 2 points. Imagine that you don't have these 2 points. In this case, there will be, this is approximate. I don't know if this is exact or not, but imagine that you can split this set of points minus these 2 with this linear function with very, very, very narrow margin. If you formulate this problem with a moderate value of C, this would be the solution. The norm of the, by the way, what would be the norm of this weight vector? When the margin is very, very narrow, what would be the norm of the weight vector? The narrower the margin, I can't hear you. Very big, the larger. The narrow the margin, the larger the norm. It's 1 over. It's narrow, it's very steep. So you will have a solution with a very high norm and no point entering into the wall. You see? Unless C is very, very big. Well, very big, let me think. No, the other way around. Unless C is very small. Because if C is small enough, what happens if I let points enter into the wall? The wall gets big, gets wider. The norm decreases. But you have to pay a penalty. Each point that enters the wall, it's a value of C that adds into the criterion. You see? So depending on the value of C, you will prefer separating the points, even with very, very, very narrow margin, if it exists, or getting more and more points get into the margin and widen the wall. You understand that? That's very important because at the end, you have to select the parameter C in your model. What will happen if you have 2 Gaussians? In 2 Gaussians, in 1 dimension, the supervector solution for this problem would be a wall between the 2 Gaussians. How wide this wall would be depends on C. It's okay? the value of C, or the equivalent parameters, because there are several formulations, the role of this parameter is to allow more or less points to violate the correct classification. And there is no general rule for that. Okay? From the mathematical point of view, the problem is very, very similar to the previous one, with more variables, more complex. But at the end, you can modify this problem. You can modify this problem, go through it. You have more complicated restrictions, but at the end, even with soft margin, still, well, we need to redefine the, let me find it. New definition. Any point that before we had equality to 1 to define supervector. Now it's equality to 1 minus the corresponding chi value. In practice, this corresponds, is summarized here. But I mean, I better explain with the graphic, and you can have a look here or anywhere else. Let me explain, sorry. In this general formulation, we have two kinds of supervectors. Two kinds of supervectors. The supervectors that just touch the wall, which is this, and this. These four will be supervectors of one kind. All this is explained in the outputs of the implementation of supervectors as well. This is one kind of supervectors, and the other kind of supervectors are the ones that go into the wall, which are this red point, this other red point, this blue point, and this blue point. The difference between one and another is the value of alpha and the value of C. Sometimes what you obtain in the implementations is only the value of alpha, because in fact it's the only you need to compute the important things. And in this case, the difference can be seen because the alpha value this is the important thing. The difference between one kind of supervectors and the other kind of supervector is that one of them have values between 0 and C, and the other one have the value exactly of C. And the points whose value of alpha is 0 are the ones which are nothing. The solution doesn't depend on this. So you solve a problem, you fix the value of C, the algorithm gives you the alphas. The points which alpha value equal to Z are one kind of supervectors. The other ones between 0, excluding 0, and C are the other kind. Okay? And that's what you need to know to properly interpret the output of the algorithm, the implemented algorithm for super vector machines. Okay. This is just an overview of the problem. We are going to stop here, but I just want to comment very briefly on what we will be having a look in the next class. In the next class, we are going to finish the slides. Finish the class, which are, I don't know, 3, 4, 5 slides, and I will try to prepare everything to have a look at the implementation of supervector machines we have in scikit-learn. I will try. But let me comment on the extension to nonlinear problems, because the first extension is to non-linear separable problems, as in the previous case. But now we have to take into account that interesting problems need non-linear boundaries in general. Okay? And what we have been introducing here are linear functions. How can we extend this to non-linear problems? Can we do something similar to the multi-layer perceptron? Can we put layers of supervector machines? Well, we could try, but I mean, you have to observe that this optimization problem is very much more complex than the previous one. This is not feasible. But the idea to use these models in the nonlinear case comes from another point of view. If you remember, we were talking about generalized linear functions. Do you remember that? We can take the input, map this input into, for example, computing cross products between the inputs. We can obtain quadratic classifiers. This can be seen as a mapping. We can map the input to another space, and then this other space, a linear function in this other space corresponds to a quadratic function in the original space. Well, this idea can be generalized using what we call kernels. In fact, we can use these mappings, arbitrarily complex mappings, in such a way that we can even map the input into spaces of infinite dimensionality. We can even do that, because we are going to have to have this mapping in an implicit way. This trick, this method, is what we call kernels. Kernels can be applied to supervector machines and also to other things in machine learning. In fact, you can have a look at kernel methods, and you will see that you have this idea applied to other parts in machine learning. What we are going to have a look in the next class is to kernels, how kernels can be applied to supervector machines, and this is the implementation we have in scikit-learn. Soft margins and kernels all together. Okay? See you next Wednesday.